Confidence intervals for estimating the population mean, sigma unknown. Whether we have a small sample case with a normal population and sigma unknown, or a large sample case with sigma unknown, we can no longer use the regular z-score formula in order to estimate this problem as a normal distribution and compute our confidence intervals. Even though our populations in both of these cases are assumed to be normally distributed, we are now estimating sigma using S, our sample standard deviation. Therefore, we will now use the appropriate interval estimate formula, which is based upon the t-distribution in order to construct our confidence intervals. The t-distribution is a family of probability distributions that is very similar to the normal distribution. The t-distributions depend upon a parameter known as the degrees of freedom. The degrees of freedom is always equal to the sample size minus 1. As the number of the degrees of freedom increases, or the sample size increases, the difference between the t-distribution and the standard normal probability distribution decreases. In this slide, Anderson, Sweeney, and Williams did a great job of illustrating how we have our normal curve, and with only 10 degrees of freedom, which means that our n value had to be 11, our degrees of freedom is always n minus 1, our curve is further away from the normal distribution. However, when our n value was 21, which means our degrees of freedom was 20, the value actually gets closer to the standard normal. As the degrees of freedom continues to increase, we would actually have the same curve as the standard normal distribution. Accordingly, our formulas for case 3 and 4, with sigma being unknown, will utilize the t-distribution instead of the z-score distribution, normal distribution that we used in the last section. For a large sample case with sigma unknown, our formula is very similar to the formula that we use for sigma known. The two differences, instead of using z alpha over 2, we have t alpha over 2 here in this formula. And since sigma is unknown, we have to use S in order to estimate sigma. With case 4, it's our small sample case with the normal population and sigma unknown. This formula is exactly the same as the formula used in case 3. For this formula, the only thing that is unfamiliar to us, or the only thing that should be unfamiliar to us, is the t alpha over 2 value in this formula. In the past, given a sample set of data, we learned how to compute the sample mean and how to compute the sample standard deviation, and we know that n is simply the size of our sample. Before continuing, we should note that if we have a small sample case and the population is not normally distributed, we can't move forward with any type of statistical analysis. Recall, for a large sample case, regardless of the original population, the central limit theorem allows us to assume that the sample mean is still normally distributed. However, with a small sample case, since we don't have the central limit theorem to stand on, if we don't have the knowledge of the population being normally distributed, The researcher must return to the drawing board and collect a sample that is at least 30. With the large sample case, they would be able to proceed using large sample formulas, whether sigma is known or unknown. Moving forward, we have our steps for computing T alpha over 2. By definition, T alpha over 2 is the T value with the upper tail area of alpha divided by 2. In step 1, we compute alpha as 1 minus our confidence coefficient. In step 2, we compute our upper tail area. This upper tail area is computed as alpha divided by 2. In step 3, we compute our degrees of freedom as n minus 1. In step 4, we go to the t-chart and find the t-value with the upper tail area as computed in step 2 and the degrees of freedom as computed in step 3. The corresponding t-value is our T alpha over 2 value. Example 4. A random sample of 81 checking accounts at a bank showed an average daily balance of 300 and a sample standard deviation of 120. Develop a 99% confidence interval to estimate the mean of the population of all account daily balances. For this problem, we have a large sample case with n being equal to 81. Sigma is not known. In fact, in this problem, they actually tell us that the standard deviation that they're providing is the sample standard deviation. So sigma is not known in this problem. So for this problem, it's case 3, a large sample case with sigma unknown. So our confidence interval formula should be x bar plus or minus T alpha over 2 times S over the square root of n. We know our x bar, our S, and our n values, so we should proceed with computing our T alpha over 2 value. For this problem, we want a 99% confidence interval. So in computing T alpha over 2, we start by computing alpha as 1 minus 0.99, our confidence coefficient, which equals 0.01. We then compute our upper tail area as alpha divided by 2, or 0.01 divided by 2, which equals 0.005. We then compute our degrees of freedom as n minus 1. So for this problem is 81 minus 1, which equals 80. So we go to our t-chart and we look up our upper tail area of 0.05, and we go down our degrees of freedom until we get to our degrees of freedom, which in this case is 80, and they meet up at the t-value 2.639. Therefore, our T alpha over 2 value is 2.639. So if we plug all of our information into this problem, our x bar is 300, our T alpha over 2 is 2.639, our S value is 120, and our n value is 81. Now, if we compute the error section of this problem, we obtain 35.19. So our confidence interval is 300 plus or minus 35.19. Subtracting 35.19 from 300, we obtain 264.81. And adding 35.19 to 300, we obtain 335.19. So we can state that we are 99% confident that the population mean daily balance at this bank is between $264.81 and $335.19. Example 5. Cal University published that their average class size is 16 students. We randomly sampled classroom rosters for some classes and obtained the following class sizes. Compute a 90% confidence interval for the population mean size at Cal University. Assume that class sizes at Cal University are normally distributed. For this problem, our sample size is 7. However, our standard deviation as well as our sample mean are not given in this problem. With a sample size of 7 and the knowledge that the original population is normally distributed, the fact that we were given no information about the standard deviation definitely indicates that our population standard deviation is not known. We learned formulas in previous sections that help us to compute the sample mean and the sample standard deviation for our data. Nonetheless, this is case 3, and the formula that we should be using for confidence intervals for this case is x bar plus or minus T alpha over 2 times the sample standard deviation over the square root of n. You should return to the sections on computing means or standard deviations in order to compute the mean and the standard deviation for this data. If you use the formulas in these sections, you'll find that the sample mean for this data is 20 and the sample standard deviation is 4.62. Now we need to determine our T alpha over 2 value, and at 90% confidence, our alpha value is 1 minus 0.9, which equals 0.1. Our upper tail area, alpha over 2, is equal to 0.1 divided by 2, which gives us 0.05. And our degrees of freedom, n minus 1, or 7 minus 1, equals 6. If we go to our standard t-table or student t-table and look up the upper tail area 0.05 and 6 degrees of freedom, we'll find that the corresponding t value, our T alpha over 2 value, is 1.943. Therefore, our confidence interval formula, we plug in our x bar value, our T alpha over 2 value, our sample standard deviation value, and our n value, and we obtain an error for this problem as 3.39. So our confidence intervals should be formed as 20 plus or minus 3.39. This gives us an interval from 16.61 until 23.39. So we can state that we are 90% confident that the true population mean class size at Cal State University is between 16.61 and 23.39. So according to our analysis, their published reports of having a class size of 16 is not accurate. Now let's get some hands-on practice. The staff at Cal Specialty submits reports about the number of sales made each week. A sample of 65 reports showed a sample mean of 19.5 sales made per week, with a sample standard deviation of 5.2. Construct a 90% confidence interval for the population mean number of sales made for the staff. You should pause the video at this time in order to compute this problem. For this problem, it was a large sample case with n being 65. Since they told us in the problem that the sample standard deviation is 5.2, we know that sigma is not known. So a large sample case with sigma unknown is case 3, and the formula you should have used is x bar plus or minus T alpha over 2 times S over the square root of n. At 90% confidence, your alpha value is 0.1. Your alpha over 2 is 0.1 divided by 2, or 0.05. Your degrees of freedom is n minus 1, or 65 minus 1, which equals 64. If you go to the t-distribution chart and look up this upper tail area and degrees of freedom, you'll find that our T alpha over 2 value is 1.669. Therefore, we can plug our x bar into our equation, our T alpha over 2 value, our standard deviation value, and our n value. And if we compute the error section of this problem, we obtain 1.08. So our confidence interval should be computed as 19.5 plus or minus 1.08, giving us a confidence interval from 18.42 up until 20.58. So Cal's specialty should be 90% confident that the population mean number of sales made for the staff is between 18.42 and 20.58.